Good morning, students. Today we will discuss about the evaluation order of SDD, that is Syntactic Direct Definitions. Okay, so here the outline of this today's class is we will discuss about evaluation order of SDD. Then after that, what do you mean by dependency graph and topological sorting. Okay, so for a given annotated path tree, so how we'll write the sorting, topological sorting for that. So then after that, we will discuss about different classes of syntax directed definitions. Then in that, these are the two classes, that is S attributed definition and L attributed definition. Okay, so this is the outline of today's class. The evaluation orders of SDD. So in previous class we have discussed about how do we construct an annotated parse tree. Okay, so then after that how we will pass that is how we will evaluate that synthesis attribute, and how we will evaluate the inherited attributes. All those things we have discussed. If you know all those things, so easily we can evaluate the order of SDD. So the evaluation order to find the attribute values in a parse tree using semantic rules can be easily obtained with the help of dependency graph. Okay, so evaluation order, so that is which attributes comes first or which attribute value comes first. So then after that, which attribute value comes next. Okay, so that is nothing but a evaluation order. So one after the other. Okay, to find that one. Okay, so we need one thing, that is dependency graph. So first we will discuss what is by dependency graph. Then after that we will evaluate the order for SDDs. Okay, so here while annotated parse tree shows the values of attributes. Okay, so here the annotated parse tree, we have already constructed a number of annotated parse trees. So in that it shows the values of attributes. Okay, so what is the S value, what is that, F value, what is that? The annotated parse tree, when it represents a parse tree with values, that one we will call it as an annotated parse tree. Okay, so it means annotated parse tree values, it shows the values of an attributes, but with the dependency graph will helps us to determine how those values can be computed. Okay, so this dependency graph, it will show how that particular value is computed. Okay, so that is nothing but a dependency graph. So we'll come to that dependency graph. Then what do you mean by dependency graph? A graph that shows the flow of information which helps in computation of various attributes values in a particular parse tree is called dependency graph. Okay, so when the graph shows the flow of information, that flow of data in the graph, with which helps in computation of various attribute values. So it shows the what happens in dependency graph. It shows the flow of data. Okay, so from which attribute value is going to next attribute. Okay, so here we know that inherited attributes and synthesized attributes. In synthesized attributes, the values of attributes goes from, that is bottom to top. Okay, so that is nothing but so it shows the flow of that data. It shows the flow of that values. That means nothing but a dependency graph. Okay, so and how the suppose a plus b. Okay, so that is a c tends to a plus b. So that is how we will compute the c value. So that is that by adding a and b value. Okay, so that one will be a showing in this dependency graph. Okay, then an edge from one attribute instance to another attribute instance indicate that the attribute of the first is needed to compute the attribute values of the second. So when you have that line or an edge from one attribute to another attribute, so with that arrow mark, so it means so that the attribute of one value is computed with the help of the attribute of another. Okay, so that one we will call it as a dependency graph. So here we will have a one simple example. So here we have a productions E tends to E1 plus T. Okay, so this is the production. So for that we have semantic rule is nothing but E dot val, that is the value of E is computed by adding the value of E1 and with value of T. Okay, so that is E dot val is equal to T dot val plus E1 dot val plus T dot val. Okay, so like that, this is the semantic rule. So now when you in an annotated parse tree, okay, so this is an annotated parse tree what we have. Okay, so here in this dotted lines, it shows the annotated parse tree. So okay, so this is the this is the active parse tree. Okay, so this is the parse tree. So these edges, okay, thick edges, that edges what we are calling as a dependency graph. Okay, so here the value of E is computed by value of E1 and value of T. Okay, so value of E1 and value of T, using that we are computed the value of E. Okay, so that is the dotted lines along with the nodes connected to them represents the parse tree. These dotted lines, these dotted lines are parse tree, and the shaded nodes represents as val with solid arrow originating from one node to another end is called the dependency graph. So it means this dependence, the flow of data. So data. So in dotted lines we don't know. So which data, data is passing from which node to another node. Whether it is from E to E1 or E1 to E, we don't know. So, but in this dependency graph, we will easily tell that the value is passing from E1 to E. The value is passing from T to E. So, because we have an arrow with solid edge we have. So, that's why, so with the help of dependency graph, how the data will be flowed, we can easily identify. Okay, so that one we will call it as a dependency graph. Okay, so here we will take one example. Obtain the dependency graph for the following annotated tree. So in previous class also for inherited attributes. So for that we have taken same same grammar. Okay, so using this grammar, so we already how to construct annotated parse tree, all those things we already know. Okay, so here how we will represent that dependency graph in that tree. Okay, so here this T tends to F T dash and T dash tends to star F T1 dash, T1 dash to epsilon and F dash to digit. Okay, so here this is an annotated parse tree they have created. Then after that we will have a dependency graph. See here. Okay, so here we have this is an annotated parse tree. How we have constructed, I have discussed in previous class. I won't discuss that one. I am discussing only dependency graph. Okay, so here how data is flowing. So here we have this is the first node. Okay, so this is the first node and this is the second. Okay, so here initially the data will be flowing from digit to F. So here we have an F tends to digit 1. See here we have F tends to digit. Okay, so it means the data is flowing from. Okay, so here data is flowing from digit, that is 1 to 3. Okay, that is digit dot lex val is equal to F, that is F dot val is equal to digit dot lex val. Okay, so here data is flowing from 1 to 3 and here data is flowing from 2 to 4. Okay, so that is digit dot lex val, that is F dot val is equal to digit dot lex val. Okay, that is nodes identified numbers. Observe the following points about the dependency graph. So here nodes identified by number 1 and 2 represents the attribute lex val, which is associated with two leaves labeled digit. Okay, so these are the starting digit value. So this is the basic digit value. So those digit value will pass to F. Okay, so here F is in this node 3. Okay, F dot value digit dot lex value will be moved to F dot val in the node 3 and node 4. Okay, so that is, so node 3 and 4 represents the attribute value associated with two nodes labeled F. So it means that digit lex value is moving to F dot val and digit lex value is moving to F. So that is 1 to 3 and 2 to 4. Okay, so then after that this 3 value is passing to T dash. Okay, so this 3 F dot val is passing that value to inherited T dot. Okay, so here using this grammar, T dash tends to F star F T dash we have. Okay, so here this is T tends to F T dash. This value is inherited attribute, we have discussed that one. Okay, so this F value is copied to T dash. Okay, so F value is copied to T dash. So then after that we are multiplying that 3 star 2. Okay, so this value will be multiplied with this 2. Okay, so here that is that resultant will be copied, will be in the T dash. Okay, so that is, so this is this from inherited t dash, okay, and this f dash t in t star t dash star f, okay. So it's t dash star f. So using these two things, I have, in this we have created a value of t dash, okay. So here this is the sixth one. So then this inherited sixth value will be copied to this synthesis t dash, okay. So that is we have this t dash star f, okay. T dash star f we have, see here, t1 dash star f. So that is t dash star f, it's to t1 dash, okay. So that one, t dash star f, we have t1 dash. This t1 dash will be copied, that value of that inherited t1 will be copied to set t dash of synthesis. Then after this copy to t dash, then after this copy to root of t, okay. So this is the last node. Like that, the data is passing from one node to another node, and finally it will end with t, ninth node, okay. So this one we will call it as a node 5 and 6 represent the inherited attribute t dash dash, which is associated with each of the non-terminal distance. So it means the data is passing from here, okay. The data is passing from here 1, okay. So like this it will come. So then after that it will come here, then after that it will joining, and after that it will goes to like this, okay. So in addition to that, here also data will come and join, okay. So this one we will call it as a dependency graph. So it means how data is flowing from one node to another node, showing that one, we will call it as a dependency graph, okay. So next one is topological sort, okay. So you already know that in the C programming, topological sort. So here this topological sort of a directed graph is a sequence of nodes which gives the order in which, okay, so which gives the order in which the various attribute values can be computed in a parse tree. So here to compute a particular value, okay, in an annotated parse tree, okay, so we will have it two or more ways to compute that value, okay. That sorting we will call it as a topological sort, okay. So using this dependency graph, we can write the order in which we can evaluate various attributes in the parse tree. So once we write the dependency graph, so easily we can write the an order in which we can evaluate the various attributes, which are, first attribute, after that next attribute, which are after that next attribute. So that sorting, that order will be done using this topological sort. This ordering is nothing but the topological sort of the graph. There may be one or more orders to evaluate the attribute. For each attribute evaluates, so for a particular annotated parse tree, we may have two or more topological sorts, okay. So here, if the dependency graph has an edge from A to B, then the attribute value corresponding to A must be evaluated before evaluating attribute value at node B. Okay, so if the dependency graph has an edge from A to B, then the attribute corresponding to A must be evaluated before evaluating attribute value at node B. Okay, so here suppose if we have a, see here, we'll have one same parse tree we are taking. Okay, so here same parse tree with the dependency graph. So how we will evaluate this topological sort? See here. So from this topological sort, so which values we have evaluated first? Okay, so here usually what we have done, so we are starting from, okay, so here digit, okay, this digit and this digit, okay. So here this is the node number 1, node number 2, okay. So then after that, this digit value is copied to F, okay. So this digit value is copied to F, that is 3, and this digit value is copied to 4, that is, it means 1 2 3 4 we have done. Then after that, what we have done, this 3 F value is copied to t dash of inherited. This is the 5th one. So then after that, what we have done, okay, so then we are multiplying this t dash with star F, okay. So that result is stored in this t dash, okay, that is the 6th. Then this t dash value will be copied to synthesis attribute of t dash. Then after that, 6th after that this 7th, that value is copied to synthesis of T dash. Then after this is the 8th. Then after the T dash, we are copied to 9th. Okay, so this is one topological sort. Okay, so this is the first topological sort what we have discussed. So like that, we may have one more topological sort, or another topological sort is also there. Okay, so but the evaluation, final evaluation is same only. Okay, so here what I have done, so here we have taken first and 2. So instead of that I will take first, then after that 3. Okay, this one I will take in first and 3. Okay, so then after that I will take 2 and 4. No issues. Okay, so what I have done, we have copied this one to F, and after that we have copied this digit value to F. No need. Then after that the same thing. After that this value 3 will be copied to, that F value will be copied to inherited T dash, that is 5th. Then after that same thing, 6th, 7th. After that T dash value will be copied, that is a multiplication of T dash into F. Okay, so that result will be copied to inherited of T dash. Then after that this one will be copied to T dash of synthesis. Then after that we will go for 8th and 9th. Same thing, 6th, 7th, 8th, 9th. That is another topological. We may have one more also. Okay, so here, okay, fine. In this third one, in this third, first one 3, 1, 3 we have taken. Okay, so then after that we can copy that F value to T dash of inheritance. Okay, you can copy it. Okay, because we are not doing any addition till that, any addition or multiplication, whatever. We are not doing any arithmetic operation. You can copy that one. Okay, so after that 1, 3. Okay, so 1, 3. Then after that 5. Okay, done. Then after that 2, 4. Okay, so after that 2, 4 from digital X value to F. Okay, you can do it. That is also no issues. Then after that, so this multiply T dash star F, that result will be 6th. Then after that 6th, after that 7th, 8th, 9th. Okay, so answer. Like that, we may, for any one dependency graph, we may have n number of topological sort. Okay, so we may have n number of topological sort for the given dependency graph. But if you want the topological sort, then there is no cycle in the dependency graph. Okay, if cycle is there, then we can't do a topological sorting, does not exist at all. Okay, the topological sorting does not exist in that for a given dependency graph. Okay, so if there is no topological, if there is no cycle in that grammar, then we will have a topological sort. Okay, so that is nothing but a topological sort and a given annotated fast. Okay, so next one is classes of SDD. Okay, next one, classes of SDD. What are different classes of syntax directed definitions? Here there are two different types of classes. One is S attributed definition, another one is L attributed definition. Okay, so S attributed definition and L attributed definition. So what do you mean by S attributed definition and what do you mean by L attributed definition? So here these are the two classes that guarantees the evaluation of an order. Okay, so then what do you mean by S attributed definition? An SDD that contains only synthesized attribute is called S attribute definition. Okay, that syntax directed definition, if it contains only an synthesized attribute, so it means that synthesized attribute means the child attribute values will be, that is the parent attribute values will be generated using child attributes. So that is bottom up order to evaluate a particular production or whatever it may be, a tree. So we will go from bottom to top. That one we will call it as an S attribute. So if all the attributes present in that SDD are synthesized attribute, then we will call it as an S attributed definition. Okay, so in an S attributed STD, each semantic rule computes the attribute value of a non-terminal that occurs on LHS. Suppose if we have E tends to, okay, so if we have a productions E tends to A plus B. Okay, so this is the productions. This is nothing but a left hand side production. That one we will call it as a head. Okay, so that one we will call it as an head. Okay, so here, so that is this is a, each semantic rule computes the attribute value of a non-terminal that occurs on LHS of the productions. Okay, so this is the LH of the productions, that is nothing but a head of the productions, what you are calling, with the help of the attribute values of non-terminals on the right hand side of the productions. Okay, so with these are the nothing but a right hand side of the productions, that is nothing but a body of the productions, what you have learned. So this head of the productions value, this head of this productions will be computed, the head production value will be computed with the body of the productions. This body of the productions are nothing but a plus b, these are the non-terminals. Okay, so here this value, when you compute the e value with the help of a plus b, so then that one we will call it as an S attributed definition. If in the semantic rules like that, so then you can easily tell that this one will be then S attributed definition. Okay, so we'll call it as a S attributed definition. Okay, so here this is an example of S attributed. So we already constructed the positive for this. So S tends to En. So this is also okay. So here S tends to En. So S tends to En. So this is S dot val is equal to E dot val. Okay, so that E dot value is copied to S dot value. So that is a body of the production value is copied to head of the production. So like that for all, this is this body of the production E1 dot value plus T dot value, that one will be a result will be copied to E dot value. That is right side of the production's value is copied to left side of the production. That is body of the production value will be copied to head of the production. So that one is called as an SDD, syntactic direct definition. In that we will have an S attribute definition. That one will call it as an S attributed definition. Okay, so here when an STD is okay, so here like that we will have a different same thing. So all values will be copied from body to head. That's all. Every value will be copied to body to head. Okay, so when an S attribute is there, so then we can evaluate attribute in bottom up node of the parser. Okay, we will bottom up of the, for this, for example, if I take this one, so that is E tends to, okay, so E tends to E plus, that is E1 plus T. Okay, so when I evaluate this one, so E dot value and T dot value, okay, then E dot value. Okay, when I evaluate these things, so then from bottom to top we are going. Okay, so that is nothing but a bottom up parser when you have a synthesized attribute. Okay, so here this S attribute definition can be implemented during the bottom up parsing, since the bottom up parse corresponds to a post order traversal. Okay, so if we are doing that bottom up parser, means that is nothing but a post order traversal. Okay, you already know that post order traversal. A post order traversal corresponds to exactly the order in which LR parser reduces a productions of the body right hand side to its head. Okay, so this post order traversal are nothing but the same as LR parser reducers. Okay, the attribute can be evaluated very easily by performing the post order traverse of the parse tree. Okay, so here the attribute values can be easily computed using the post order traversal. This is a post order traversal. Okay, so how will post order traverse? This is the algorithm for each child C of n from left. Okay, so that is the a child will be the a post order. It means, so post order is nothing but left, right, then go to root. That's all. Okay, it's left, right, root. Okay, so this is the in evaluation of that post order. Okay, so the evaluation of that S attribute definition. Okay, so it means S attribute definition is nothing but if the attributes in a production, if attributes or values are synthesized attributes, then we will call it as a S attributed definition. Okay, so in that we will use the bottom up approach. Okay, so when you have a bottom up approach, then we will have to evaluate, we will have a post order traversal, left, right, and head. Okay, so that is S order. Okay, so next after that, what do you mean attribute grammar? Okay, so what do you mean by attribute grammar? Okay, an SDD without any side effect is called an attribute grammar. A pure grammar without any side effect. Okay, the grammar, if it is contains without any side effects, then we will call it as an attribute grammar. Okay, so that the semantic rules in an attribute grammar, okay, the semantic attributes in an attribute grammar defines the value of an attribute purely in terms of the value of other attributes and constant. Okay, so the semantic rules in an attribute grammar defines the value of an attribute purely in terms of the value of other attributes and constants. Okay, so it will get the value from other attributes and the constants only purely. Okay, so then attribute grammars have the following properties. They don't have any side effect. Okay, so here suppose if you take one tablet, as if it is not having any side effect, then it is pure tablet like that. If it doesn't have any side effect, then we will call it as a attribute grammar. It is a pure grammar. They allow any evaluation order consistent with dependency graph. They can evaluate any order, evaluation order for consistent with dependency graph. Okay, so this is an example we have in attribute grammar. So for this grammar only we have constructed an annotated past. This is one example of an annotated attribute grammar, pure grammar. Okay, so you don't have any side effect in that. Okay, so next one is L attribute definition. Okay, so what do you mean by L attribute definition? So here, if it is SDD contains a synthesized, then we will call it as a S attribute. So now it contains L attribute definition is nothing but if it contains inherited and also synthesized, both if it is there, then we will call it as an L attribute definition. Okay, so here this is an L attribute definition is a second class of SDD. The idea behind that is between the attributes associated with the production body. Okay, so between the attributes associated with the production body, the dependency graph edge can only go from left to right. Okay, so dependency graph can go from left to right, but not right from right to left. So it means the dependency graph, suppose if you have a A tends to ft dash, whatever it is, star ft. Okay, so if you have like this, okay, so ft dash, whatever it may be. Okay, so this value should go from left to right, not right to left. So it means that value will copy to here, not here. Okay, so that one will call it as an L attribute definition. And again, that is introduction. So now the definition of so here the definition one of the following. So it may be synthesized or it is inherited. It may be synthesized or it may be inherited attribute, but with the following rules. Okay, in L attribute, it may be synthesized attribute or it may be inherited attribute, anything with the following rules. Consider a production A tends to x1, x2 to xn, and let xi of A is an inherited attribute. Okay, so if you have a production A tends to x1, x2, xn, okay, so in that xi dot A is an inherited attribute. In this situation, we will have a following. Okay, so here what those rules? The inherited attribute must be associated with A, which is LHS of the production. Okay, suppose if inherited attribute is there, must be associated with the A. Suppose here we have a tends to x1, x2, x3 is there. Suppose if we have a present inherited attribute with the associated with A means the always which is LHS of the productions, head of the productions. Suppose A inherited, suppose if A tends to x1, x2, then A inherited is that always it should be a left side only. That is head of the productions. Another one, all the symbols of x1, x2, x3 to xi appearing to the left of xi have either synthesized or inherited. Okay, suppose if you have a x1, so the x2 it may be inherited or a synthesized, anything it may be. Okay, suppose if we are taking x3, so then x2 always it may be synthesized or it may be inherited. Or A inherited or a synthesized attributes associated with occurrence of xi itself, but without forming a cycle. Okay, so inherited or associate synthesis attribute associated with this occurrence of xi itself. Okay, suppose if it is taking value by itself, so but it doesn't form cycle. Okay, so I am taking value my side, but I don't have cycle one side. That one we will call it as a an is L attribute definition. So usually when you have inherited attributes are there, so at that time obviously it will be L attribute definition. Okay, so here we are taking example. So here we have a t dash tends to a star f t dash, and here we have a production t tends to f t dash. See here, suppose here we have a semantic. So here t dash inheritance. Okay, suppose if we have a t dash. Okay, so t dash inherited is nothing. We are copying this f value to t dash. Okay, so it means, so in the symmetrical we have at the left side t dash inheritance is equal to f dot value. Okay, so and here we have a, so t dash t1 dash inherited is equal to, so that is t dash star f, t dash inherited star f dot value. Observe this following thing. So in the first rules, observe that the attribute value f is denoted by f dot value. Okay, so f value is denoted by f dot value is copied into attribute value t dash. Okay, so f value is copied to t dash denoted by t dash inheritance. Okay, inheritance inh, showing that edge is going from left to right. Okay, so going from, it should go from left to right. F is at left side, t dash is right. It going from left to right. Okay, so note that f appears to the left of t dash in the production of the body. So here f is appear in the left. So we already that is it may be it's synthesized or a inherited attributes. If you have x, if you have xi is there, either it may be synthesized or inherited. Okay, so our inherited attributes must be associated with a, which is a LHS of the production. Okay, so here it will be LHS of the productions. It may be so it may be inherited or a synthesized. It is on the left side. Okay, so that is the one thing. So in the second role, okay, so the inherited attribute value of t dash and LHS. So inherited attributes t dash and LHS, head of the productions, and synthesized attribute f present in the body of the productions are multiplied, and result is stored in the attribute value of t dash denoted by t1 dash. Okay, so here what you are doing, so this t1 dash star f, that is t1 inherited star f will be multiplied, and these things will be copied to t1 dash inherited. Okay, so this is the semantic rule what we have. Okay, so here note that both t dash and f appear on to the left of t dash. Okay, so here see here this t1 dash. Okay, so this both the t dash and f are appear on the left side of the t1 dash. Okay, so that is the second row. Okay, in second row, so here all the symbols in xi. Okay, so suppose if you have xi is there, then it will be xi minus 1 will be a synthesized or a inherited attribute. So here it may be, this is an inherited attribute, this is an xi, then xi minus 1, xi minus 2, or it may be a synthesized or it may be inherited. Okay, so in each these cases, the rules use this information from above or from left as required by the class. Remaining attributes are synthesized in SSD is in L attribute. Okay, so here that data will be passed from left to right only. Okay, so suppose if you have an attribute, so at the left side you may have synthesized. Suppose if you have an inherited attribute, so at left of that attribute it may be have synthesized or it may be inherited. Okay, so the data will be copied from left to right only. Okay, so data is copied from left to right. See, in general, if it is inherited attributes is there in a SDD, so easily we will tell that we may have, you know, L attribute definition we have. Okay, so in general we will tell that, but it should satisfy these rules. Okay, so this is an L attribute values. Okay, L attribute definition. So these are the two important things: S attribute definition and L attribute definition. Okay, so this is the summary of today's class. We have discussed about how we will evaluate the order of SDD. So to evaluate order of SDD, we need dependency graph. So dependency graph, it shows the flow of data from one node to another node. And this using this dependency graph, we will represent, we will derive the different topological sort for the given past annotated past tree. That is nothing but how that values will be, how nodes will be evaluated one after the other. That one will be the a topological sort for a given grammar. For a given past tree, we may have two or more topological sorting. Then after that, we have discussed about two classes, different classes of STD. So one is S attribute definition, another one is L attribute definition. So in S attribute definitions, so if it is attribute synthesized attributes are there in the attribute, then we will call it as an S attribute definition. Okay. So then if we have a L attribute definitions, in that if we have synthesized and inherited attributes present and with the following conditions, then with that some conditions, then that one we will call it as an L attribute definition. In addition to that S attribute, we have a that pure grammar we had a, with no effect, then that one is a pure grammar. Okay, so these are the things we have discussed in this today's class.